Okay, so we will start with the lecture. Is my screen visible to you?
Yes.
Okay. So good morning everyone. Today we will be covering basics of trees and graphs. Now in this presentation we will cover some fundamental concepts of trees and graphs, like what they are and some common traversal techniques and how they are represented in code, and also some common problems based on them. So we will start. So what is a tree? So tree is a hierarchical data structure consisting of nodes that are connected by edges. And the main thing in tree is that a tree cannot contain a cycle. So you cannot if you start from a node, you cannot cycle back to that node again. You can only visit that node once. So you can consider this file system tree as a tree, or now we will look at some key terms in trees. So here we have root. So root is the topmost node in the tree. So in this diagram, we can consider this Tom folder as a root node, because every other file is present in Tom folder. So this is the root node. This is the starting point of our tree. If we want to run any traversal algorithm, we have to start from this root node only. Now, what are nodes? So, nodes are basically elements of the tree. So, elements means like in this example, we can see we have here data folder, and in this data folder, we have 1.txt, 2.txt. So, this every element in this tree is considered as a node, and also the root of the tree is a node. Now, what is an edge? So, edge is basically the line connecting two nodes. So, these arrows can be considered as edges in this file system. Now, what are parent and child? So, a node pointing to another node. So, the node that is pointing to the other node is considered as its parent, and the one being pointed is called the child. And what are the leaf node? So leaf node is a node without any children. So a leaf node doesn't have any outgoing arrow from it. So that is called as the end of a tree. So basically when you reach a leaf node, you reach the end of a tree. You have to then backtrack again. Now height of the tree. So height of the tree can be called as the longest path from the root to a leaf node. So emphasis on the longest path. So height must be the longest path that you can reach to a leaf node. So in this example, what would be the height of the tree? Can someone tell me? Three.
The distance between the root and the leaf node,
Yeah.
lowest leaf node,
So what will be the height in this tree?
3.
Three. I think it will be two.
That would be the minimum. No? It
No,
takes
no.
the maximum depth. No?
Mean, so what height is like the number of edges in a path, maximum number of edges. So
Yeah,
you can
yes.
see here is one, here is one edge, and here is one edge. So there are two edges in the maximum path. So height of
Oh,
this tree will be two,
the
right?
number of nodes minus 1. I was saying number of
Number of
nodes.
nodes minus one. So here are one node, two node,
Okay.
and three nodes. So minus one, two. So height will be two, right? Did everyone understand why the height of this tree is two? Okay, so next is depth of a node. So depth is basically reverse of height. It shows the distance of a node, distance from a root to a specific node. So here, depth of what will be the depth of nodes.txt here?
1.
1.
Right, one. Absolutely right. So these were all the key terminologies in trees. So next is comparison between trees and linked list. So you have learned about linked list, right? So what are the key differences between trees and linked list? They can be considered as same because like they both are based on pointers and memory allocation, but there are some key differences between them. So first is the structure. So a tree is a hierarchical data structure. That basically means that it is a non-linear data structure, whereas in linked list is a linear data structure. So like in tree you can have one parent and multiple children, basically giving its non-linear structure. But in linked list each node can point to only one next node. This gives its linear structure. Now uses of a tree. Now tree is used for hierarchical data, for example in file systems or expression parsing, whereas linked list is used for data storage and dynamic memory allocation, because insertion and deletion in linked list is really fast. So this is used for data storage and memory overhead. So tree has multiple pointers from parent to child. Tree is more tree contains more memory, whereas in linked list there is only one pointer to the next node or two pointers depending if it's singly linked list or doubly linked list. So memory consumption of linked list is very low. And now search efficiency. So now we will let us see what are binary search tree. But for now, basically know that searching an element in binary search tree takes just log n time. So this is better than in linked list because the worst case search time complexity in linked list is big O of n, because we have to search all the nodes in the linked list to find element. So these were the basic differences between trees and linked lists. So now next we will see how do we represent trees in actual code. Now we have two ways to represent trees in code. First we have the array representation. Now in array representation again there are multiple ways, but the most common and easiest way is that each element in the array is the parent of the index of that element. Now, here in this example, we can see that the element at index 2 is 1. So, the parent of node 2 is 1. So, here in this tree, we can see that this is the element node 2 and the parent of the 2 is 1, which is basically seen in this example. And now this minus 1 represents that it is the root node of the tree. So we it is a convention, it we can take anything 0 or anything, but just take care of handling indexing if it is 0 based indexing or 1 based indexing. Here we are considering 1 based indexing. Similarly for 3 we have its parent as 1. Here we can see for 3 we have its parent as 1, and so on for every other element in the array. For example, here the node 7 has parent 3. Here node 7 has parent 3. So this is how we represent trees in array representation. So now next is the linked representation. This is similar to how we did in linked list, but the key difference here is in linked list we only had one next pointer, that is only one pointer pointing to the next node. But here we need two pointers because we are considering that this is a binary tree. So binary tree basically means that each node will have at most two children. So we will need a left pointer and a right pointer to represent this tree in code. So basically this is similar to how we implemented representation in linked list. We had int value, but instead of node next we have two pointers, node left and right, which points to the left node and the right node. And here this is how we initialize the root node. We use the new keyword and do this construct, call this constructor with the value that we want to give to its node. And similarly we do this for all of its neighbors. So for example, we created here root 1. Now root 1, now the left child of 1 is 2. So root of left, we create new tree node 2, and similarly root of right, we create new tree node of 3. Similarly, we do this for every element in the tree. This is how we represent linked representation of tree. So next we have types of tree. Now there are many types of tree, but the main two types that we are going to study in this session are binary tree and binary search tree. Now binary trees. So binary trees basically means each node has at most two children. So each node can have one children or zero children or two children. That basically what it means. And searching in this tree is big of n, because at worst case you will have to search for every node in the tree. So the worst time complexity will be O of n. um, these are basically uh, some of the most used types of trees, you can say. Next, we have binary search trees. So, binary search trees are trees where the left subtree contains values less than the current node and the right contains greater values. So, here in this example, you can see that our root element is 8, and if you see in its left subtree, all the elements in the left subtree are less than 8, and all the elements in the right subtree are greater than 8. Similarly, for this 14, you can see its left child is 13, which is less than. And in this 6, its right child is 7, which is greater than. And this property is like very useful in solving some problems. And also searching in this tree is O of log n, because you can always eliminate half the search space like you did in binary search. It is the same concept as binary search, as dividing the search space in half. So if you want to find suppose you want to find an element 6, so now you compare it with this first root node, you see that 6 is less than 8. So by the property of BSTs, you know that 6 cannot lie on its right subtree. So you eliminate the right subtree and go to the left subtree. Now you see 3. Now 6 is greater than 3. So you know it cannot lie in the left subtree. So you eliminate the left subtree and go to the right subtree, and you find 6, and then you return. So the whole time complexity of searching in BST is of log n, which is same as we did in binary search, like eliminating the search space in half. So log base 2 of n more d. So next we have tree traversal algorithms. So there are two main types of tree traversal algorithms. One is DFS and next is BFS. So as you can see in these images, the key difference between DFS and BFS. So DFS, depth first search. So in the word itself, depth first. So we take a branch and we go to the deepest parts of that branch until it ends, and then again we backtrack and explore all other paths. So basically here we can see we start from 1, then go to 4, 5 and 6 until it ends, and then we backtrack and explore all other paths. So this is depth first search. Now in breadth first search. So breadth means like exploring level wise, which is also called as level order traversal. So we traverse all the elements in a current level and then go to the next level. So we can understand BFS and DFS using an analogy. So for example, if you are in a maze and you want to find the right path, so which algorithm will you use, DFS or BFS?
Depends on problem, right?
So if you are in a maze and you want to find a path and there are multiple paths, so which would be the better way, DFS or BFS?
Both would have the same
BFS would be better.
algorithm, right?
Which one?
Still,
Breadth first search.
Breadth first search. How?
So breadth first will search for the paths of the similar length. Like in every iteration, it searches for the paths of similar lengths. and we keep increasing the length by one each time. And at one point, we will find the exit from like only one path, which will be the shortest path.
Yeah, right. It depends on how you do it.
In best
May-
case, BFS would be better, right?
Yeah,
But
in
in
best
worst case,
case,
both are equal, right?
yeah, both are equal. So, like BFS is more controlled, right? In DFS, you just pick a random path and go down to the end, deepest ends. So, in best case, DFS will be better, but in worst case, both are same. It won't be any different in the worst case. Uh, but if we are talking about real life, you will implement DFS, right? You will just pick a path and go down the path until it ends. BFS, you maybe you can do it, but most of people will do DFS only. Now, for BFS, imagine you are exploring a building and you want to explore all the rooms in a floor. So, which algorithm will use, DFS or BFS?
BFS.
Yeah, right, BFS, right? Because you will explore all the rooms in the current floor, then go to the next floor, which is same as exploring level wise. So here BFS will be the best option, because in DFS you will have to like go up the floor again and again and come down. So this will be not efficient. So here BFS will be better. So now we will see the code snippet for DFS. Now, these 4 to 5 lines of code are one of most important code snippet in trees, because this code snippet will help you solve almost 60 to 70% of tree problems. So basically, all the problems can be traced down to this template. You just have to modify some small. Uh, you just have to modify this code a little bit to solve the problem. So now, what this function says. So if you have studied recursion, you know the template for recursion. So first of all comes the base case. That means when do we have to stop the recursion, and next comes the recursive calls, all the recursive calls, and then comes the return statement if any. Here we have a void function, that's why we don't have any return statement. But now we will try run this code on this tree. So now consider one as its root element. Now first we check the base condition. If root is null, so one is not a null pointer. So we go to the next line and call root dot left. So left of one is 2. So we go to its 2, and then again call the function. We check if it's null. It's not. So we again call root of left. Then left of 2 is 3. Now we go again in the function and check if it's null pointer. It's not. So we again check DFS of root of left. But here root of left is null. So we go in the base case and return from there. So from this null pointer that will be here, we again go to the function call of 3. And in 3 we were at this line, DFS of root of left. Now we have executed this function call. Now we'll go to the next line, which is DFS of root of right. So root right of 3 is 4. So now we will go to 4 and again check the base case. If it is null, it's not. So again these two calls will be executed and both are null. So we will return back to 3, back to 2. We will backtrack again to 2, and again we will check root of right, because we have executed the root of left part. So basically we do this for every element in the tree. And the DFS, this is how we basically traverse the DFS. But we need to like get a ordering for elements in a tree. So for this ordering, we again have 3 types of DFS. So first one is the uh, in order traversal. So basically, in order is left, root, right. So we first explore the left subtree, then we explore its root node, and then the right subtree, then the right subtree. So as you saw in this template of code, it's the same code, just one small difference. Here we have cout root of value in between the two function calls. So, uh, so this small change gave us in order traversal of a tree, basically left, root, right. So so now for this tree, if we consider A as root and start our in order traversal, we'll go to the left subtree of the A, which is B. Now B. Uh, Now we will go to C. Now C, we encounter our base case, which is the its left and right values are null. So we go back to C, and now we have executed this line. Now we go to the cout statement and we print its value, which is C, which is first printed here. Now we backtrack to B, and then we have again executed this root dot left. So we again print its value B, and we go to the next, which is D. Now we again encounter our base case because there is nothing after D. So we again go to we print D and go backtrack to A, and then then we print A, and then we go to its right subtree. Similarly, we do this for the right subtree of A, and you can see the final DFS ordering, sorry, in order ordering. So here you can see CBD. This is the left subtree of the A, and here EF, which is the right subtree of A. So we can see that everything before the root will be its left subtree in the ordering, and everything after the root node will be its right subtree. So now the use of this traversal is in binary search tree. So as we saw in binary search tree, that everything in the left subtree is smaller than the current node, and everything in the right subtree is greater than the current node. So here we saw that everything before the root node in the ordering was its left subtree, and everything after its root node was its right subtree. So basically, if we run a in order traversal in a binary search tree, we will get the ordering sorted in ascending order. So this is really useful in solving problems. Uh, because like the left subtree will always be less than the current element. So the or in order traversal of a BST will always be sorted. You can check, you can dry run on a BST. You can see for yourself. You can run an in order traversal, and you can see that the ordering always comes out sorted. The next is pre-order traversal, which is just root left right, which is similar to in-order traversal, but in code-wise we have just changed one line of code, which is we have put the cout statement before any recursive call, which is also called as head recursion if you have learned that. So basically, we visit the root node first, and then we visit its left subtree, and then its right subtree. So here in this example, we can see A is the root node. So first we directly print its value, the root node A, and then we go to its left subtree. We go to its B, then again print B because we are on this line of code cout root dot value. Then we again go to this function called root dot left, which goes to C and again prints the value C, and then we backtrack to B, and this function call is still remaining of root dot right. So we call the function for the right of B, which is D, and then we again go in this function of pre-order, check the base case, and then directly print the value D, which is getting printed here. And then we again backtrack to A, then go to its right subtree, then print E, then go to check its left subtree. If it is there, it's null, so we return again to E. Then we go to F, then print F. So this is the final ordering of a pre-order traversal. So now from the name itself, you can see it's pre-order. So we can observe that the root node is getting processed before any of its child nodes. So one advantage of this is while cloning a tree, so questions related to some cloning or creating a new tree. So because we are processing the root node first before the children nodes, we can easily clone the tree because we are creating the root node first, then we can easily create the children and join them. So this is basically used in cloning a tree or creating a new tree. This is the application of pre-order traverse. So next is post-order traversal. Post-order traversal is basically left-right route. So basically, you can see that we are processing the children nodes first, and then at last we are processing its root node. So we first visit the left subtree, then the right subtree, and then finally the root node. This again is the same snippet that we follow. We have just changed one line of code. Here cout is at after all the recursive calls. So this is tail recursion. So here first we will start from A, check if it's null. It's not, so we will call for its left B, and now we will again call it for its left C. Now it is null, but we still don't print. Sorry. Now we will see that its left and right are null, so we hit the base case. Now we print C. Now we again go to B. Now we have executed this root dot left call. We don't print anything. We just go to the next call, that is root of right. So we go to the right of B, that is D. So now again we hit the base case because the left and right of D is null. So we uh, go to this line of code, the fourth line of code, that is cout root dot value. So D gets printed. Now we again backtrack to B. Now all both of these function calls are executed. So now finally B will be printed. So here see left, right, root, C, D, B, C, D, B. Similarly for everything. So if we go to A, we don't print anything. We go to its right, we see E. There we don't do anything because we have a process its left and right child. So we don't have a left child here. So we go to its right child F. So now there are no left and right childs. So we process F. So we print F first, then we backtrack to E. Then both of his function calls are done. So we print E. Then we again go to the root node, and finally we print A. So this is basically useful where in most of the problems, because we are processing all the children of a node before processing the current node. So if we want to find some like height of a tree or something, so for that purpose we use post order traversal. And note that the last element of a post order traversal will always be the root node of a tree. So this is an important property of post order traversal. Okay, so next we have BFS, breadth first traversal, also known as level order traversal, because we visit all nodes level by level. So here in this example, you can see that on the first level there is A, second level we have B and E, and on this third level we have C, D, F. So the BFS traversal for this is A, B, E, C, D, F, A, B, E, C, D, F. Now this is a different snippet of code for this. Here we are using a queue data structure. uh, I think queue is covered already, so I will not go into detail on what this push or pop does, but you already know this. So here for level order traversal, again have our base case, which is the same. If root is null, then return don't do anything. Main difference here is uh, we are creating this queue of tree nodes where we push our current nodes. Now we first push our root node, and then we pop out the current front node, and we process all its childs, and then we print the node basically, and then we again do this for every other node in the queue. So first we will have a root node in the queue, so queue will have a. So we will pop the queue. So A will be popped from the queue. Now we print the value A. So first A will be printed. Now we will check if its left or right value exists or not. If it exists, we push it into the queue. So first we push the left value, that is the B, and then E. So now our queue will contain B and E. So the front element is B. So now we again go to this while loop. Now queue is not empty because we have B and E in the queue. So now we'll get the topmost node, front node, which is B. Now we'll pop B, print B. So here B is printed. Now we will check if the left node of B is left and right node of B is present or not. So here we have both the nodes. So we push both the nodes. So our queue will look like E, C, and D because E is still remaining to be processed. So E is still in the queue. So our queue will look something like E, C, and D. And now we will again go into the while loop. We will pop out the front element, which is E, and then we will print E, and then again check if its left or right child are present or not. Its left child is not present, so we'll push the right child. uh, so here you can observe that after A, B and E are printed, so its next level is printed. Similarly, after B and E, C, D, F, its next level is printed. So this algorithm can be used where you want to change the like structure of a tree. For example, you want to swap the nodes of a tree. For example, you want to swap B and E. You can do this with DFS, or it will be really tough to do this with DFS. But with level order traversal, you can easily swap this two nodes with each other. So this is the application for DFS. Now next we will look at some common tree problems. We are going to see three problems. We are going to see some three problems. So first one is find height. Now calculate the height of a tree. So now first tell me what is height of a tree as we saw earlier.
The maximum path length, basically, from the
Yeah,
root.
right. Maximum path, right? So try to think of an approach where we can find the height of a tree using you use recursion. Think recursively. How you can find height of a tree.
If you find null, then parent has height 1, then height is maximum of height of left child and right child plus 1.
Yeah, right, correct. So basically think. Uh, for example, see this tree. So recursively imagine that you know the height of B, height of the left subtree. Get the see this root node. Now you know the height of its left subtree and the height of its right subtree. So how will you find the height of its current node? It will just be the maximum of the left subtree height and the right subtree height plus the element itself, that is 1. So that will be the height of the subtree. So here the height of this is 1, and for similarly the right subtree is 1. So maximum of 1 comma 1 plus 1, because we are including this a also, so this one height will also be added in this. So the height of this tree will be 2. So let's look at the concepts. So this is the definition. Height of a binary tree is defined as the number of edges in the longest path from root node to a leaf node. Now alternatively, some definitions consider that the number of nodes in the longest path. So basically like height will be number of nodes minus 1. That will be the height. and the maximum of this. So for an empty tree, we are considering the height of the tree to be 0 or -1, but for simplicity, we are considering 0. So here we have our approach. Now recursively calculate the height of the left and right subtrees. So as we saw earlier, now if we have the height of the left subtree and the right subtree, we can easily calculate the height for the current node. We just take the max of the left height and right height and add 1 for the current node itself. So for this function, we need to define the base case, which is the most important. That is, if we reach a null pointer, that is null node, the height of that will be 0, right? So, for example, see here in this example, for this tree, we are running recursion. We call height of tree of 1. Now it will run. For this, we are using our post order traversal. So you can see that after the recursion call, we are processing. So this is the application of post order traversal. So here, as you saw in the post order traversal, we first process its left and right child. So here we start our post order traversal from 1, we'll go to 2, then go to 4, then again process 4. So 4, we reach our base case, that is 4 of left is null and 4 of right is null. So both the calls of those null nodes will return 0. So according to this return statement, the max of left height comma right height, that is max of 0 comma 0 plus 1. So the height of this subtree of 2 is 1, which is correct. And again we backtrack to 1, then go to its right element first before processing its root element. So now here for 3 we know that left is null, right is null. So again it will be the same, max of 0 comma 0 1 plus 1. So height of subtree 3 will be 0 again. So now what will be the height, sorry, it will be 1. So what will be the height of this 1? So it will be the height of left subtree, max of left subtree comma right subtree plus 1. So now here the height of this left subtree is 1, comma this height of right subtree is 0. So max of 0 comma 1 is 1 plus 1. So the answer is 2. So the height of this whole tree will be 2. This is correct. So here you can see the dry run of this code, which is the same that we did here. So the final height of the binary tree is 2. So now do you have any doubts in this code?
The time complexity for recursive would be of 2 raised to n, right?
No, no. So see, like we are not going on the same node multiple times. We are only exploring the same node once. So the time complexity will be n. Actually, we are visiting each node twice, but we are not taking the constant. So the actual time complexity is 2n, but we take it as of n because
Okay,
we,
okay.
right, it won't be 2 raised to n because not visiting the same node twice, multiple times.
Got that.
So the space complexity for this code is O of h, where h is the height of the tree, because like at max in the recursion stack we have to put h number of nodes, that is the height of the tree nodes. So the space complexity for this code will be O of h. Do you have any doubts in this? Okay, we will move on. So the second problem is count number of nodes. So tell me your approach. How will you approach this problem?
We keep if it's like a, a binary tree that has whose vertices value we know, like 1, 2, 3, we can keep a map or a boolean array.
Okay, but can you think recursively? How will you find number of nodes recursively?
We can add an extra argument, and every time we visit a non-null node, we increment it.
Yeah, right.
Number of nodes of left plus number of nodes of right plus one.
Absolutely correct. So the it follows the same idea as find height. So for this example, if we are in this root node A and we know the number of node in its left subtree and the number of node in its right subtree, we can easily calculate the number of nodes in this tree by just addition of this number of node in left subtree plus right subtree plus including this root node itself. So this will be plus 1 plus left number of nodes and right number of nodes. So here it will be just 6. The number of trees in this number of node in this tree will be 6. So now let's look at the approach. Total number of nodes in the binary tree is the sum of current root node, total nodes in the left subtree and the right subtree, as already we have covered. So approach. Now this is the same code as the height code. Here also we are using the post order traversal because we need to process all of its children before processing the current node. So the only difference between here is that we are using this return statement. That is the only difference in this because the base case is the same and all. So instead of taking max of both, we are just taking the summation of both. That is the main difference to count nodes. So here in this example, this is the same example. We can see we call the function for root node 1, then we go to its left node, and then we again go to its left node, and we uh, left and right node is null, so we hit base case. So now from both this function we return for this function calls for null values, we return 0. So the return statement will be 1 plus left, that is 0 again, plus 0. So the number of nodes in this subtree will be 1, which is correct. So we return this to 2. Now the right call for this is still remaining, so we don't process this node. So we go to its right subtree and we go to 5, and we again go to null null, then we return 0 0, and the number of nodes in this subtree will again be 1. So now 1 will be returned to 2. So now we have our left number of nodes and right number of nodes, which is 1 and 1. So for this subtree of true, the number of nodes will be 1 plus 1 plus 1, that is 3. So there are 3 number of nodes in this subtree. So now 3 is returned to 1 according to this code. So now we have processed this left count. Now we go to its left right count. So for right count, we go to right of 1, which is 3. And now again we hit our base case on this node values left and right. Again we return 0 0. We will get 1 plus 0 plus 0, which is 1, which is the number of node in this subtree. Then we return 1 from 1 to the root node. So now for the root node, we will have its left count as 3 and right count as 1. So according to this return statement, we will have 1 plus left count, which is 3, plus right count, which is 1. So 3 plus 1 plus 1, it will be it will be 5. So the total number of nodes in this tree will be 5. So now the time complexity for this code is same. because it is the post order traversal only. So the time complexity of this code will be O of n, as each node is visited once to be counted. So the time complexity is O of n, and similarly the space complexity is O of h, because the recursion stack will contain h at most the height number of nodes, number of nodes which is equal to the height of the tree. That will be the worst case space complexity for this. Now, do you have any doubts in this code or approach or anything? Okay, so we'll move on. So the next question is count number of leaf nodes. So count number of leaf node. So what is a leaf node? Can you tell me?
No children.
Yeah, right. No children. So its left node is a null pointer and a right node is the null pointer. So we just need to count how many of such nodes exist in the tree. So it is same as the count number of nodes. We just tweak a small thing. We just add one more base case in the code. So here we have our code. Here you can observe that we have added one more base case here, which is if root of left is null and root of right is null, we return 1 because that is a leaf node. This just returns us if a node is a leaf node or not, if you view it separately. So the approach is simple: traverse the entire tree as we did. It is the same post order traversal, and check if a node is a leaf or not with this line of code. And if it is, return 1. Else you can else count recursively, similar to what we did in find height and count number of nodes. We check the number of leaves in the left subtree and number of leaves in the right subtree, and then we just add them both together. Here we are not adding plus 1 to anything, because uh, because the current node main cannot be a leaf node, so we don't consider it as a leaf node, so we don't add 1 in this return statement. So only the leaf node in the left subtree and the right subtree is getting added. So let's look at the walkthrough of this code. So here we have the same tree, and here nodes 3, 4 and 5 are the leaf nodes, as you can see, because they don't have any children to them. So according to our code, we'll call 1, then we will follow the post order traversal, which you should be able to do on tree without looking at any code or anything. So we just go to its left child, then for this 2 we again go to its left child 4. Now we see that according to this base case, we first check this base case, that if root is a null pointer or not. So now 4 is not a null pointer. So we'll go to the next line of code, and here we see that root of left is null and root of right is null. Here we can see both are null. So here we return 1 from this function call. So now similarly we go to the right call, which is for 5, and again we check the base case. If it is null, no. Then again we go to the second line. Now left and right both are null in this case. So for 5 both are null. So we again return 1 from this both the function calls. So for this it will simply be number of leaf nodes in the left subtree and right subtree, which is just 1 plus 1, which is 2. So similarly, we again go to the backtrack to the root node and go to its right node. And here 3 is again the leaf node. So we return 1 from here. So for 1, 1 will be the number of leaf nodes in the left subtree plus right subtree. And now in the left subtree we had two leaf nodes, and right we had one. So 2 plus 1, 3. So the final total number of leaf nodes will be 3. So do you have any doubt in this? The time complexity is again the same. We go of n as we are visiting all number of nodes only once, and the space complexity is also same. We go of h, basically the height of the tree. Uh, this is the worst case time complexity. So do you have any doubts in this?
No.
Okay. Okay, finally. So we are starting with graphs. So what are graphs? So similar to trees, graphs are non-linear structure. They consist of vertices or nodes. It is same as node, and edges. Edges are same as trees. The line connecting two nodes. Edges connect pair of vertices. So now graphs can be seen as a real world example. Your social groups, like your friend circle, can be considered as a graph. So you as a person can be called as a node or a vertices, all the person in your friend groups, and the friendship between them can be called as an edge. Now here we will see some key terminologies in graphs. So here we have a vertex. Vertex is a node in the graph. So similar to that friend group analogy, each person in that graph can be considered as a vertex. And edge is the connection between two vertices. So for example, if two person are friends, then we can consider that there is an edge between those two friends. So that is called as an edge. Now directed graph. So edges have direction. So it can be like friendship can be one way. So you may consider someone as friend, but someone may not consider you as friend. So that is directed graphs because it has direction. It can be one way or two way. Whereas in undirected graph can be considered where there is no direction. So both of you are friends. So undirected graph is just a directed graph, but both have like two nodes have both on outgoing and ingoing edges to both of them. It can be considered as that. Now weighted graphs. So edges may have weights. So you can consider like how much friendship do you have with your friend. That amount can be considered as a weight in a graph. Now, what is the difference between graphs and trees? So basically, a tree, it can be considered as a graph, but the main difference is that the tree is a connected graph. Connected just means that if you start from one node, you can explore all other nodes from that node only. But in graph, it may not be necessary that you can go to all other nodes from a single node. You may have to travel start traversal from multiple nodes to explore all nodes in a graph. And also one more difference is that tree cannot contain a cycle. So basically if you start from a node, you cannot come back to that node again in a traversal. Whereas in the graphs are more flexible. So the graph can contain cycle. You can visit multiple nodes, a node multiple times. And next, cycle, as we discussed earlier, trees cannot contain cycle. It's by their definition. Whereas graph can contain cycle, and trees must be connected. No components are there in tree. Graphs can be connected or disconnected. Now edge count. Now the maximum. There, if there are n nodes, there are exactly n minus one edges in a tree. And because we want to connect every other node, right? So we will need n minus 1 edges to connect the tree. Now for graph, it can range from anything to 0 to n into n minus 1 by 2 for undirected, because the number of edges are cut in half, uh, while as in directed, uh, both on outgoing and incoming edges can be considered different. So that's why we have n into n minus 1 edges in a directed graph. Now in tree, parent-child relationship. Now every child has only one parent, so there is only one way for going from parent to child. Whereas in graphs there is no strict limitation on parent-child relationship, as uh, there can be multiple ways to go from multiple nodes to other nodes to a single node. So there can be multiple parents for a single child in a graph. And tree also has a root node, which is a starting point defined defined prior to the definition of tree. Whereas in graphs there is no concept of root. You can start from any node. You can consider any node as your root node. So this was the comparison between graphs and trees. So how do we represent graphs in code? So again, we have two ways to represent graphs in code. We have adjacency matrix, which is a 2D matrix where matrix of ij denotes that if it is 1, then there is an edge between the node I and j. So for in this code snippet, you can see that there are three nodes in this graph, 0, 1, and 2. And according to this matrix, you can see that 0 of 1 is 1. So there is an edge between 0 to 1. Here you can see 0 to 1, there is an edge. Similarly, for second, we have 1 of 0 is 1. So there is an edge from 1 to 0. You can see 1 to 0. And for the second node, we have 2 comma 1 is 1. So there is an edge from 2 to 1. Now in second way to represent graphs in code is adjacency list. Please mute yourself. Okay. Adjacency. The second way to represent graphs in code is adjacency list, uh, which you will most probably see in most of the questions. It is the most common way to represent adjacency list. Now, the adjacency list is a list of lists where each index contains the neighbors of vertex. So basically, in this snippet of code, we can see that this 0 index, we have this array which contains 1. So the neighbors of vertex 0 is just 1, which can be seen in this graph, that the neighbor of 0 is 1. So there is an edge from 0 to 1. And similarly for this, these are the neighbors of vertex 1. So neighbors of vertex 1 is again 0. So there is an edge between edge from 1 to 0. And for neighbors of vertex 2 is 1. So there is an edge between 2 and 1. Now you will ask which one to use for representing code. So now it depends on the graph. So for example, if you have a dense graph, so for example, there are multiple like multiple edges to multiple nodes. So for example, if we had a dense graph, so for this 2, we had a edge to 1, then to 0. Then for big graphs, we had suppose 3, 4, 5. Then again, 2 was connected to all of them. So basically, it was dense. There are more number of edges in this graph. So for this purpose, we will use a matrix. because using a vector of vector, that is list of list representation, will have memory overhead, because we will have to save redundant data, because if it is undirected we will have to again and again save for both of them, their both of their edge representation. So for dense graph, adjacency matrix will be more efficient memory wise, and if it is a sparse graph, we can use adjacency list, because the memory overhead won't be that much. And also, uh, like, while if we will see that traversal techniques of BFS and DFS, in a dense graph, adjacency matrix will work just fine, because like almost all of them will have one or one only. So BFN running BFS and DFS on adjacency matrix will be better. But in case of in case of sparse graph, running BFS and DFS on adjacency matrix will uh, unnecessarily increase our uh, time complexity, because we will have to explore all the elements in this array. So basically, BFS complexity of BFS and DFS will reach n square, because we will have to traverse all the elements in this adjacency matrix. Whereas in this adjacency list representation, we don't have to traverse n square number of nodes. We can just traverse all the elements in this list that are present, and we can run our BFS and DFS in linear time only. This was all about representing graphs in code. Next, we have types of graphs. So now we have four main types of graphs. First, we have directed graphs. So directed graphs basically have a specific direction from one vertex to another. This represent a relationship which can be one way or two ways. If we have a double edge like this, 0 to 1 and 1 to 0. So these are directed graphs. Now undirected graphs do not have any direction. Connection are bidirectional and relationships are mutual. Now the third type is weighted graph. As we saw earlier, this is how we represent them. We write the weight of the edge above the edge. So each weight have assigned weights, and it can represent a cost, a distance, or anything. So these are uh, weighted graphs can also be the directed graph or undirected graph. There can be directed weighted graph or undirected weighted graph. So for this, for example, is an undirected weighted graph. Next, we have cyclic and acyclic graphs. So this basically means that if a cycle contains, if a graph contains cycle, then it is a cyclic graph. So for example, all these were a cyclic graph, whereas this graph is a cyclic graph because there is a cycle in this graph. So next, we have graph traversal algorithms, which is the most important part of graphs. So here again we have the same two algorithm, which is depth first search and breadth first search, which is the definition of both of them is the same as it was in the tree. Depth first search, we take a branch and go until the deepest ends of that branch, and then again we backtrack. And breadth first search is we just traverse all the immediate neighbors of a node, and then we again travel the immediate neighbors of those nodes. So and also the code for them is similar. So for DFS we have depth first search. So DFS explores as far as possible along each branch before backtracking. So for example, take this graph for an example. This is the adjacency list representation of the graph. This is the graph that we are going to see. And this is the code snippet for our DFS traversal. So let's now understand each line. So first we have our function definition. In that we pass our current node that we want to explore. And here we have the adjacency list. This is how we represent, uh, and we have our vector pool of visited. Now, why do we need a visited array? Yes, what is your doubt? Sarvesh. Okay, where were we? Huh. So why do we need a visited array? Can someone tell me?
So we don't fall in a cycle.
Yeah, absolutely correct. So we don't fall in a cycle. We don't visit the same node multiple times again and again. So for that purpose, we maintain a visited array. So basically, after we have processed a certain node, we mark it as visited and only explore other nodes if it's not visited. So this we run DFS using a recursive function. So basically we use the recursive stack for running DFS. So here we can see we need two things, a recursive stack and a visited array. So now we will dry run this code one by one. So let's now consider 0 as our root node for simplicity here. It's not necessary that you consider 0 as a root node. You can start DFS from any node. For example, you can start from 4 or 3. It doesn't matter. So first line of code is visited of node is true. So we have processed this node and we mark it as visited. So we don't come back to this node again. So we first start from 0. We mark visited of 0 as true. So here we have start at node 0. We push our 0 into the stack. We mark 0 as visited. So this will be our current visited array. 0 will be true and all other values will be false. Now process node 0. So now we see out the node 0. So our traversal will DFS traversal we first have 0. Then we check all the neighbors of 0. So for neighbor in adjacency of node. So if you remember, this adjacency of a node gives us the list of neighbors of that node. So for every neighbor of node, we check if it's not visited. If it's visited, we don't do anything, we just go to the next neighbor. But if it's not visited, then we run the DFS. We recursively call for that neighbor and adjacency and pass the visited array, and then we again go to this DFS function. So for example, if you consider one edge, we neighbors of 0 is 1 and 2 and 3. So we push 1 2 1 2 and 3 in the stack. Right now we pop 1 from the stack. So now the stack will contain only 2 and 3. So now so we call our function for 1 comma adjacency comma visited. Now we will again mark 1 as visited. Now visited of 1 is true. Now we see out 1. Now we again run this for loop. We'll check the neighbors of 1. So here we don't have any unvisited neighbor for 1. So we don't do anything, and we again return to the zeroth call. That is the call for DFS call for zeroth node. So again in this for loop, we have we from the stack we can see we have 2 in the top element. So we pop 2 from the stack, and now the current stack will look like something like 3. Now mark 2 as visited, as we saw. Mark 2 as visited, cout node, that is cout 2, and then check the neighbors of 2. Now 2 has only one unvisited neighbor, which is 4. So now we push 4 into the stack. So here we have push its unvisited neighbor 4 into the stack. So stack will look like 4 comma 3. So now we pop node 4 from the stack. So now the stack will look like 3, and now we process this node 4. So now we mark 4 as visited. this will be the current visited array. All of them is true except for 3. And now we process node 4, like output 4, and again we can see here that 4 doesn't have any unvisited neighbors, so we don't do anything. So now finally we have our top element as 3. Now we pop 3 from the stack, and now we mark 3 as visited, and all of the values are filled with true, so all of the graph is visited. So now we have completed our DFS. So now we print 3 and again check if 3 has any unvisited neighbors. So there are no unvisited neighbors. So we end our DFS. Now the final ordering will be 0, 1, 2, 3, 4, or it can be 0, 1, 2, 4, 3. It doesn't matter. Like the exact ordering may vary based on how you push your neighbors into the stack. For example, if I pushed 0, for example, if I push 2 before 1, uh, sorry, 1 after 2, then 2 will be on the top of the stack, right? So 2 will first get popped, and all of the neighbors of 2 will get pushed into the stack. So the ordering may change based on how you push your elements into the stack. So the ordering does not matter that much. It only depends on how you push your nodes. Okay. So the time complexity for this DFS is big O of n only. Uh, to be specific, it is big O of v plus e, where v is the number of vertices and e is the number of edges. Because of this for loop we are running. So for this recursive function is iterating on every vertex. So that is v, and we are also iterating over each edge. So that is plus e. Note that it is not times e because of this visited array. Because of this visited array, we are only visiting each node once. So each edge will be traversed only once. So the time complexity for that will be big of v plus e, if you want to go into detail, but it is the linear time complexity of big O of n, you can consider it. And the space complexity is big O of n because of this visited array and the adjacency list. We don't consider this adjacency list, but this visited array we consider big O of n, and also because of the recursive stack. So this was all for DFS. Next we have PFS. So as we saw in trees, PFS, we called it as level order traversal. So this is the same. We traverse level wise. So in graph, level wise means that we traverse all the immediate neighbors of a node. So for example, in this example, you can see we have here 0. So the immediate neighbor of 0 is 1 and 2. So we first traverse 1. See here, first we traverse 1, then we traverse 2, or vice versa. You can do anything. The ordering of neighbors doesn't matter, but it should be the neighbors of the current node only. So here is the code snippet for BFS. It is similar to how we did in trees, but the difference is again here we have a visited array for the same thing, that we don't fall into a cycle. We don't process nodes multiple times. So again we maintain a queue and we push our start node into the queue, that is the root node. Here we consider 0 as a root node and we mark visited 0 has visited. So visited of 0 equals to true. So now we go into this while loop. So in this while loop, we are just taking the front element of the queue and popping the front and basically processing the node, that is printing the node. And for every neighbor, we are just pushing it into the queue. So because of the FIFO nature of the queue, only the immediate neighbors of the node are getting processed. whereas in stack we had LIFO, last in first out. So the it was expanding depth wise, but here it is expanding breadth wise because of the FIFO nature of the queue. So for the same example, so this example here, we start from BFS from 0. Now here is the initialization of the visited array queue and our final BFS ordering. So now step 1 is start at node 0. We mark 0 as visited, then we push its neighbor into the queue. So we push 1 and 2 into the queue. So the queue will become empty. Now we check for neighbors of 2. So neighbors of 2 we have only 3. Unvisited neighbor 2 is 3. So we'll put sorry, so is already visited. So this can see if it's not visited, then we are pushing it in the side we are making it late. If it is already visited, it means that it was already in process. So we are not again processing it. We just skip. This will be the current queue, and this will be the visited state of the visit. And our current BFS ordering is 012. Now then we again DQ 3, that is front of the queue, and mark it as visited. Now we will check for unvisited neighbors of 3. So here we have 4 as an unvisited neighbor of 3. So we will push 3 into the queue. Sorry, 4 into the queue. So we have pushed 4 into the queue, and the BFS ordering for current state will be 0, 1, 2, and 3. Now step 5, we will pop out 4 from the queue, mark 4 as visited. Now we will check for neighbors of 4. So neighbors of 4, we have 3 neighbors, 0, 1, and 5. But only unvisited neighbor of 4 is 5. So we push 5 into the queue. So we pushed 5 into the queue, and then uh, this is the current BFS ordering, and this is the current state of visited array. Now the final step is we pop out the node 5 from the queue and mark it as visited. Now 5 has no neighbors, so we end our BFS there. So uh, all the values in the visited array are true, so we have completed the BFS, and also the queue becomes empty. So we have reached our base case, that is while queue not empty. So we will jump out of this while loop, and then we finally print our BFS ordering. So the final BFS ordering will be 0, 1, 2, 3, 4, 5. Here similarly the BFS ordering can vary with how you push your elements into the queue. So a single graph can have multiple DFS or BFS ordering. So that was all from my side. Do you have any doubts regarding anything, trees or graphs? You can ask me.
Topological sort is there in our question.
What?
Topological sort
Topological sort?
is
No, we have decided to drop that. That will be a bit advanced.
okay.
Do you have any doubts? You can put it in the chat or unmute yourself. Okay, so we have a surprise for you.